In this video, I will discuss the organic chemistry questions of IIT JEE 2012 paper 1. In this question, the type of hybridization of carbon atoms in alene has been asked. So, to answer this question, you have to know the structure of alene. The structure of alene is something like this: C, H, H, double bond C, double bond C, H, H, like this. So, now you can see the central atoms, the central carbon atom has 2 pi bonds and 2 sigma bonds. It is very similar to an alkyne. So, the carbon atom of alkyne, you can see here also we have 2 pi bonds and 2 sigma bonds. That means very similar. So, we know that the hybridization of an alkyne is sp. So, the hybridization of the carbon atom of an alkyne is sp, and similar to this, the hybridization of alene, the central carbon, is sp hybridized, and for this one, these 2 terminal carbons are sp2 hybridized. So, if you check if you try to understand the 3-dimensional structure of alene, you have to go here, you have to check this structure. You can see that the central carbon, which is sp hybridized, has 2 pi orbitals, which can 2 p orbitals, which can laterally overlap with the nearby p orbital of other carbons. So, here it is overlapping with the left hand side carbon, and here it is overlapping with the right hand side carbon. So, this 2 p orbital of the central carbon is actually 90 degree or perpendicular to each other. Now, that means the 2 hydrogens of the left hand side will be on the plane which is perpendicular to the p orbital. That means one hydrogen will be above the plane of this paper, is here, another hydrogen will be just below the plane. But in this case, for the right hand side carbon, right hand side terminal carbon, both the hydrogens will be on the plane of the paper, like this, because the p orbital of the right hand side carbon is just perpendicular to the plane of the paper. So, this is the 3-dimensional structure of alene. So, now if we have to select an option, we have to select the option where we have one sp and an sp2. So, option B will be the correct option for this question. In our next question, a reaction scheme has been shown, and it has been asked that how many aldol condensation reaction is possible to get this product. So, now we have to check the whole mechanism of the process, what is going and what is going on throughout this process. So, if you check, I already have written the mechanism here. We have the acetaldehyde here in presence of the base, which is taking a proton from the acetaldehyde, and we are getting a carbon ion here, which is stabilized due to the nearby carbonyl carbon and the oxygen attached with the carbonyl carbon. And then in the next step, this CH2 minus is actually attacking the carbonyl carbon of the formaldehyde. So, and in the next step, we are getting this as a product. So, this is one aldol condensation. So, this whole process is just one aldol condensation. So, one aldol. This is the number 1 aldol condensation. Next is what? Next, there is another alpha carbon attached. So, the hydroxide, which is already present in the system, is going to take this hydrogen, and then the corresponding carbon ion will react with the formaldehyde and will give something like this. Okay. Here also we have another alpha carbon, alpha to the carbonyl group. So, this will be again taken by the base. Similar to the previous case, here also the newly formed carbon ion is going to react with the formaldehyde and give you this one. So, until or up to this step, there were 3 aldol condensation. So, one was this one, then here is the second aldol step, and then here is the third aldol step. Now there will be no more aldol condensation reaction, because we know that in case of aldol condensation reaction, an alpha hydrogen which is with respect to the carbonyl carbon is necessary. That means we have seen that in acetaldehyde we have 1 alpha carbon and 3 alpha hydrogen which was attached with the CHO group. So, this 3 has been replaced or has been abstracted. This 3 proton has been abstracted by the hydroxide group and 3 aldol condensation has happened. But now we can see that in the product, after the 3 aldol condensation step, there is no alpha hydrogen present. So, the carbon is alone, there is no hydrogen attached with this carbon, although there are 3 CH2 group attached with this carbon, but not any hydrogen. That means there will be no removal of hydrogen in presence of the base. So, no more aldol condensation is possible, but we are getting a product which is different from this one. This is not the product. That means another reaction will happen which is not aldol condensation. The next reaction that is going to happen is crossed Cannizzaro reaction, which I have shown in this section. If you check very carefully, you can see that the OH group now is going to attack the carbonyl carbon of the formaldehyde, and there will be an hydride which will be coming out from the formaldehyde and is going to attack the carbonyl carbon of the aldehyde which is created in the last step of the 3 aldol condensation reaction. And then there will be a negative charge here, and this negative charge is going to take a proton from the medium to form our final product. So, this step is not an aldol condensation, this is a crossed Cannizzaro reaction. This is a crossed Cannizzaro reaction, not an aldol condensation. So, how many aldol condensation were there in this whole process? 3 aldol condensation were there. So, option C will be the correct answer. In this question, it has been asked that how many optically active product will be obtained after complete ozonolysis of this compound. So, complete ozonolysis means all the double bond present in this compound will be broken, and we know in an ozonolysis reaction the double bond will break and a carbonyl carbon will form at these ends. That means what is going to form after the complete ozonolysis? I am writing the product one by one. So, if the first double bond, this is the first double bond, if this breaks, then we will get something like this: CH3, CH, double bond O. Fine. Similarly, from the other end also, we will get another CH group. So, CHO, C, CH3, H, again CH. So, the second double bond is now breaking. So, we will get another carbonyl here, double bond O. Then again in this end another carbonyl group, C, H, CH3, single bond CHO plus again another carbonyl, so CH3. Now, if you check, all these compounds are kind of symmetric, they have a plane of symmetry. As all these compounds are symmetric, So, all the compound will be optically inactive. So, all these 4 products will be optically inactive. So, the correct answer for this question will be option A, that means 0. So, there will be no optically active product after the complete ozonolysis of this compound. In this question, we have to identify the binary mixture that can be separated into individual compounds by differential extraction as shown in the given scheme. So, if you check the scheme, you can see that we have to select a pair of compound or a set of compound which can be separated by using sodium hydroxide solution as well as sodium bicarbonate solution. That means, one of the component of the mixture or one of the component of the 2 compound mixture will be soluble in sodium hydroxide, other will not be soluble in sodium hydroxide. Similarly, the same set, for the same set, one compound will be soluble in sodium bicarbonate and another will not be soluble in sodium bicarbonate. To answer this question, we need to know about the solubilities of different kind of compound. So, let me write it down here like ROH, where R is an aliphatic group. So, this is just an alcohol. This is not soluble in sodium hydroxide or sodium bicarbonate. So, sodium hydroxide and sodium bicarbonate insoluble. Next is this carboxylic acid and this carboxylic acid. That means aliphatic and aromatic carboxylic acid. Both are soluble in sodium hydroxide as well as sodium bicarbonate. And sodium bicarbonate soluble. Next is aromatic OH, that means phenolic OH. This is soluble only in sodium hydroxide. So, sodium hydroxide soluble and sodium bicarbonate insoluble. Okay. Now look at the options. In first option, we have a phenol and a benzoic acid. So, phenol and benzoic acid both will be soluble in sodium hydroxide because yes, aromatic OH and aromatic carboxylic acid. So, both will be soluble in sodium hydroxide. So, the first route, that means separation using sodium hydroxide solution, will not work here. That means this option is cancelled. What about option B? In option B, we have benzoic acid and benzyl alcohol. That means we have an alcohol like where the OH group is connected with an aliphatic carbon. So, it is insoluble in sodium hydroxide as well as sodium bicarbonate, and we have an acid, a benzoic acid, which is soluble in sodium hydroxide and sodium bicarbonate. That means option B is a correct option. So, this set of compound can be separated using the 2 method, that is sodium hydroxide solution as well as sodium bicarbonate solution. What about option C? We have an aliphatic alcohol, so ROH, which is insoluble in both sodium hydroxide as well as sodium bicarbonate, and we have an aromatic hydroxide like this, which is soluble in sodium hydroxide but insoluble in sodium bicarbonate. That means if we use the first route, that means sodium hydroxide solution only, we can easily separate compound 1 and compound 2, because compound 1, that means the aliphatic alcohol, is going to be insoluble in sodium hydroxide, but AROH or phenol will be soluble in sodium hydroxide. So, we can separate it, but we cannot separate it using sodium bicarbonate because both are kind of insoluble in sodium bicarbonate. So, this one as well as this one will be insoluble in sodium bicarbonate. So, we cannot use or we cannot take this option is cancelled. Now let us check option D. Here we can see again benzyl alcohol, that means an aliphatic OH group. So we have to check it is insoluble in sodium hydroxide as well as sodium bicarbonate, and then we have a carboxylic acid group. Any carboxylic acid group, be it aliphatic or aromatic, will be soluble in sodium hydroxide as well as sodium bicarbonate. So sodium bicarbonate and sodium hydroxide soluble group, so it can be separated using both the method. That means we can separate it using a sodium hydroxide solution as well as a sodium bicarbonate solution. So option D is the correct answer. So option B and option D are correct for this question. In this question, it has been asked that among these 4 options, which will be unstable at room temperature, or which are unstable at room temperature. So there could be more than one correct answer. So to answer this question, we need to know that how a compound, this kind of compound, can be unstable. So if the compound is anti-aromatic, then it will be unstable at room temperature. Now what is anti-aromatic? Let me correct the spelling. Anti-aromatic. So anti-aromatic means it must be cyclic, planar, with 4 n-pi electrons. So cyclic, planar, 3, 4 n-pi electrons. Okay. So if these 3 criteria are satisfied, then the system will be anti-aromatic and will be unstable at room temperature. So let us check. With the first option, we have 6-membered ring, so it is cyclic obviously, and the number of pi electron. So if I consider n is equal to 1, then we have 4 pi electrons. So fine, it is going with our 4 in pi electron rule. But is it planar? No, it is not planar, because these 2 carbon are sp3 hybridized. So this system is non-planar. So we cannot apply the anti-aromatic rule here. So let us check here. So in option B, we can see that we have a cyclic system. Fine. Yes, it is planar because all the 4 carbons are sp2 hybridized, and the number of pi electrons is 1, 2, 3, 4. So it is satisfying our 4 in pi electron rule, where n is equal to 1. So if we consider n equal to 1, then we have 4 pi electron, which is going with our 4 in pi electron. So all the 3 criteria are matching. So option B is one of the options which would be unstable at room temperature. In case of option C, we have a cyclic structure, a planar one, but we have 1, 2, 3, 4, 5 pi electrons. Now the problem is, in this, although we are counting 5 pi electrons, but we have an electronegative atom oxygen connected with the system. So this will actually take the pi electron from the carbon, and it will stay like this. So the structure will be like this, O minus and plus. Now if you check, it has a cyclic structure. It is planar because all the carbons are sp2 hybridized, and we have 4 pi electron in this case also, 1, 2, 3, 4, because the pi electron from this carbon has been taken from it by the oxygen atom. So this one is also anti-aromatic and unstable at room temperature. So this is one of the correct answer. Now if we check option D, we can see a cycloheptane system, where it is also connected with a oxygen atom which is electronegative. So it is going to take the electrons and it will form something like this. So we have the heptane system, cycloheptane system, with a positive charge here and oxygen negative charge. Now if you check, the number of pi electrons will be 6, which is not 4n pi electrons. It is 4n plus 2 pi electrons, where n equal to 1. So 4n plus 2 pi electrons. So this is also not anti-aromatic. So it is cyclic planar, but the number of pi electrons is 4n plus 2. So we can say that only option B and C will be correct for this question. In this question, it is asked that the substituent R1 and R2 for 9 peptides are listed in the table given below. How many of these peptides are positively charged at pH 7? So pH 7 is neutral pH, and at this pH, if the peptide wants to be positively charged, then it must have an amine group, not just any amine, an amine connected with a CH2 atom, because amine could also be connected with a CO group. In that case, that amine, the electron pair will not be available with the nitrogen. It will be resonance stabilized, so it will go away, it will be delocalized by the carbonyl oxygen. But we need an electron pair, because if it has the electron pair available, then only it can acquire a proton from the solution at pH 7, and it can generate a positive charge. So acquiring a proton from the solution or from the aqueous solution, and it will look like this. So when there is a CH2NH2 group present in the peptide, then that peptide will be positively charged at pH 7. So we have to check between Rn and R2, or we have to check the R1 and R2 substituents if there is some CH2NH2 available. So look here, in 1 we have hydrogen, so there is no CH2NH2. In 2 also we have H and CH3, no CH2NH2, but in 3 also we have CH2COOH as well as H as R2, so there is no CH2NH2. In option 4 we have CONH2. We are not looking for CaONH2, we are looking for CH2NH2, but yes, in option 4 R2 we have a CH2NH2 group. So this option is going to show a positive charge at pH 7. Now if we go forward, in option 5 we have CONH2, which is not going to abstract proton. In both R1 and R2 we have CONH2, so it will not work. In option 6 we have a CH2NH2 here, so this will have a positive charge, and also R2 has a CH2NH2, so this is going to have a positive charge definitely. Option 7 we have a CH2COOH as well as a CONH2. CONH2 is something which is not going to take proton, because the lone pair will not be available in nitrogen, so it will not have the positive charge. Similarly, carboxylic acid is not going to accept proton, it is going to donate proton but not accept proton. Option 8, yes, in option 8 we can see a CH2NH2 as R2, so this will have a positive charge. In option 9 we have another CH2NH2 group present here, so option 9 will also have a positive charge. So option 4, 6, 8 and 9 is correct option for this question. Here in this question, it has been asked that when the following aldohexose exists in its D configuration, the total number of stereoisomers in its pyranose form is. So basically here we have to keep in mind about these 3 points. One is the D configuration, the total number of stereoisomers, and the pyranose form. Okay, so now look at the structure. I have drawn it, I have redrawn it here below actually. So if we count the carbon, this is 1, 2, 3, 4 and 5. So it will be in D configuration. That means the last chiral carbon in Fischer projection, or the bottom chiral carbon in the Fischer projection, will have the hydroxide group in the right hand side and the hydrogen in the left hand side. So it will be in D form. So the last chiral carbon is actually locked in its D form. We cannot change the stereochemistry here, because according to the question it will be in D configuration. Now we have to make the pyranose form. Pyranose means a 6-membered ring with an oxygen connector. So we have to do it like this. We have to erase this hydrogen and we have to connect this oxygen with the carbon, number 1 carbon here, and we have to change other few things, like we have to change this carbonyl O group to OH. So now we have to calculate the number of chiral carbon. So we have a new chiral carbon here due to the formation of this hemiacetal, and we already had 1 chiral carbon here, another here, and the 5th, which was chiral carbon, but it is now locked in D configuration. We cannot change the stereochemistry of this chiral carbon. So the number of chiral carbon which may change the stereochemistry is basically 3. So the total number of possible stereoisomers will be 2 to the power n, where in this case n is equal to 3, that is number of chiral carbon. So 2 to the power 3 is equal to 8. So although the compound has 4 chiral carbon, we can take only 3 because the system is locked. The 5th chiral carbon is locked in D configuration. So we cannot take that in count. If you have liked my video, please click the thumbs up button as well as share the link with other people. And for more videos, please subscribe my channel and press the bell icon. Most importantly, please comment below about your needs related to chemistry so that I can make more videos on several other topics.